Welcome back, and we're going to continue our journey in Chapter 18 looking at the analysis of salts. This time we're going to start looking at some instrumentation and spectroscopy, which is new to us. So let's get started. Spectroscopy is a technique that we will learn more about also in Year 12. It's defined as the study of molecular structure and dynamics through the emission, absorption, or scattering of light. Basically, it's the way that we can interpret information about a substance by using light, either shining light through it or some part of the electromagnetic. So what this means is, regardless of the type of spectrophotometer or spectrometer that we're using, we need to have a light source, some sort of light source, that will then be shone through the sample, okay, and where we usually select a particular wavelength, okay, remembering that we have our spectrum of the electromagnetic spectrum where we start with red through to violet, and then remembering that our red is low energy, violet being high energy. So we have different levels of energy within a single beam of white light. This passes through the sample, and then we can detect changes in that light and use it like a fingerprint for different substances. All of this can occur, if you remember back to atomic structure, because atoms and molecules absorb energies of some wavelengths and transmit others. So they have discrete energy absorption depending on their electronic structure or the way that they are bonded together. By passing the sample with energy, so light of different wavelengths, we can produce an absorption spectrum. And you may remember this from our studies in flame colors and electron absorption earlier in the course back in ECP. So we get an absorption spectrum that is produced by the absorbed radiation. This can be because it causes the bonds to stretch. Okay, so this diagram here where the bonds are stretching out, bend, twist, or various other different things. We will look at different types of spectroscopy throughout the rest of this course and into Unit 3-4. But there are a number of different types that cause the molecules to react differently to different types of energy. So whether it be the nucleus, where we see nuclear magnetic resonance, or the bonds, which we see with infrared, or the electron transitions, which we see with atomic absorption, which is what we're going to be learning about today. So the electromagnetic spectrum covers a continuous range of energy, okay? So from radio waves, which are very large, low energy waves, through to gamma rays, which are short, damaging radiation rays. Our visible spectrum lies within that, okay, remembering that ultraviolet is above the energy. So this is actually looking at a increasing energy going from right to left. Okay, we're decreasing in energy towards the red. So the energy forms different parts of the spectrum and can be used in different spectroscopic techniques. So down here we have NMR, which is like your MRI, which we'll learn about in Year 12. Here we have X-rays, damaging radiation, and then within this we have our ultraviolet radiation, which is what causes us sunburn, infrared, which allows us to see at night, so those night goggles and stuff often use infrared sensors, and then the visible light spectrum, which covers all the different wavelengths of light that make up our visible light spectrum. So we have seen and discussed this before. You may remember the spectrometers that used when we did this flame test back in ECP. This light that we see changing color is due to the fact that outer shell electrons are absorb energy and are excited to higher energy levels. So when they come back down, that energy is spat back out with a particular wavelength corresponding to the energy of the transition. So if this is a high energy transition, we will see light in the violet or blue region. If it's a low energy transition, we see it in the red region and the orange. This emitted light is always a specific wavelength, and color because it moves back down to the ground state or the lower energy level. So we can excite the electrons. Some of them will come back down, sort of like a toddler on a sugar high. When it comes back down, it spits out light of a particular wavelength. This provides what we've talked about before as an emission spectrum. We get these bright bands of light that are emitted at particular wavelengths that correspond to those transitions. Because there's multiple transitions available in any one particular atom, we see a series of lines, which is like a fingerprint that allows us to identify what that atom was. This is an emission spectrum, okay, because we're measuring the light that is emitted. Okay, so we get an emission spectrum. And we often see this used in identifying things like elements present in stars and things like that. So there are a few advantages and limitations to this, however. There's only a few elements that produce flame colors in a Bunsen flame like we saw in class, okay? So some elements just aren't excited in that region. The flame color we don't get a color because it's not hot enough to excite the electrons within those atoms, or the wavelength is not visible. It might be visible in the infrared, or it might be visible in the UV, and we can't see those with our eyes. And sometimes what we get is ambiguity if we're just looking at colors. And you remember we looked at some who were quite similar, because we see things where we get a strontium produces a scarlet flame, lithium produces a crimson flame, calcium produces a red flame. These are all red, but they can be difficult to differentiate between. So, and emission spectra can often have bright lines that are hard to interpret, many different lines. So what we tend to do is, rather than look at emission and look at the color that's being produced, we can tune this in order to get a much more accurate and precise measurement known as atomic absorption spectroscopy. And we will cover that in our next video.